Hello students. In the last classes, we were deriving the equations of electric field and magnetic field of moving point charge. We obtained the equations like the electric field of a moving point charge to be equal to E bar of R bar comma T equal to Q by 4 pi epsilon 0 R divided by R bar dot U bar the whole cube into C square minus V square into U bar plus R bar cross U bar cross A bar. So this is the equation of electric field, and the equation of magnetic field was found to be B bar equal to 1 by C into R cap cross E bar of R bar comma T. So from this equation you can write the equation of magnetic field as well. So let us have a brief idea about the concepts that are contained in these equations. First of all, given this equation of electric field of a moving point charge, let us try to find the equation of electric field if the charge is stationary. So we know that equation is already provided by the Coulomb's law. So let us check whether this equation, if used properly for a stationary charge, will give us the right equation. So we are looking for the electric field of a stationary charge, and by stationary we means that its velocity is 0. So how would this equation change? We have plenty of terms with velocity here. Since velocity is 0, the acceleration will be 0, and the U bar, which is C R cap minus V bar, will be simply C R cap. We know U bar is equal to C R cap minus V bar. If the velocity of the charge is 0, U bar will be C R cap. So in the second term you can see that we have R bar cross C R cap. Since both of them are in the same direction, its cross product will be 0, and the last term will be simply 0 if you take the case of a stationary charge, or simply because the acceleration is 0, you can say that the last term will be 0. Now coming to the the first term, here we have U bar, which is C R cap minus V bar. For a stationary charge, it will be simply C R cap. So let us substitute for the case of a stationary charge. The electric field can be found to be equal to Q by 4 pi epsilon 0 R divided by R bar dot, here we have U bar. U bar will be simply C R cap. So C R cap the whole cube multiplied by C square minus V square. Again V square is 0. So C square minus 0 into U bar is C R cap. So this will be the equation of electric field. Now we have R bar dot C R cap. R bar is R cap, right? So R cap dot C R cap will be simply RC. Since R cap dot R cap is equal to 1, here inside this bracket we have simply R into C. So this is equal to Q by 4 pi epsilon 0 R divided by RC the whole cube into C square into C R cap, which is C cube into R cap. So this term C cube and C cube will cancel out, and it will be simply 1 by 4 pi epsilon 0 Q divided by R square into R cap. So this equation is simply the Coulomb's law, right? So we have found that if we substitute into the given equation of electric field of a moving point charge the case of a stationary charge, then we will have the Coulomb's law in our hand. So we can say that the equation that we have derived, which is the electric field of a moving charge or a dynamic charge, is a generalized equation of the Coulomb's law. It actually contains the case of a stationary charge as well as the case of a moving charge or a dynamic charge. So because of this, since we obtained the Coulomb's law from the first term of this equation, sometimes The first term of this equation is called the Coulomb field. So because that term yielded you the Coulomb's law when we substituted for V equal to 0 case. So this is also called the generalized Coulomb field. And since this part contains the terms of velocity, this first part of this equation is also called velocity field. So these are the peculiarities of the first term of this equation. The first term is called velocity field, or it is called generalized Coulomb field. Now coming to the second part, in that term, the term of acceleration comes. And hence, this second term is called acceleration field. The first term is the velocity field. It is due to the velocity, or even if it is stationary, the first term will be contributing to the electric field. Now if it is accelerating, charge is accelerating, the second term will appear, and hence it is called the acceleration field. Now let us look at the dependence of the velocity field and the acceleration field on r. So if you look at the velocity field, you can see that the terms containing r comes here and in the numerator and in the denominator. So you can see that r divided by r cube. Velocity field is dependent on r divided by r cube, which is equal to 1 by r square. So you can see that if a charge is moving with, if we consider the velocity field, its dependence on r will be 1 by r square. It will fall like 1 by r square with distance. Velocity field. Now coming to the acceleration field, if you look at the acceleration field, in the numerator we have r into r, and in the denominator we have r cube. So what is the dependence of acceleration field on r? So acceleration field will fall like, or will depend on r like r square by r cube, which is equal to 1 by r. So acceleration field will not fall as soon as the velocity field. It will have a gradual decline. It falls off like 1 by r. So when we come into later parts regarding the concepts about radiation, we will see that it is this field, this acceleration field that falls like 1 by r, that actually contributes the radiation. So this acceleration field is also called radiation field because it is this part of the electric field of a dynamic charge that is actually contributing the radiation, the electromagnetic radiation from accelerating or oscillating charges. So these are the concepts that we have to remember when we consider this term. We saw that there are two terms, and first term is either generalized Coulomb field or velocity field, and the second term is acceleration field or radiation field. Now let us also write the generalized equation of Lorentz force from the given set of equations. So we know the Lorentz force is given by the total force, which is QE plus Q into V cross P. The second part is the Lorentz force due to the magnetic field, and this can be considered as the total force acting on a charge. Now let us substitute for electric field and magnetic field from the given sets of equation. A lot of terms will be common. So if you consider a test charge Q, test charge capital Q, which is at the vicinity of a moving charge small q, what will be the force acting on this test charge Q? That is what we are looking for. So the small q will be contributing electric field and magnetic field due to its dynamic properties, and the capital Q charge is under consideration. So instead of the small q here, we will have to substitute capital Q because that is our test charge here, and electric field and magnetic field are due to the small q, which is our moving charge. So let us write down the equation. So this is equal to Q into capital Q divided by 4 pi epsilon 0 into R divided by R bar dot U bar the whole cube multiplied by c square minus p square into u bar plus r bar cross u bar cross a bar. So this term is the electric field multiplied by the charge of the test charge. Now let us write the equation corresponding to the magnetic field part. Here we have additional v bar cross the magnetic field. Now what is magnetic field? Magnetic field is r cap by c cross the electric field part, which is c square minus v square into u bar plus r bar into u bar cross a bar. So this is the equation: total force that is acting on a test charge capital Q, which is at the vicinity of a moving charge small q. So this can be considered as the generalized equation which gives the total force that is exerted by a moving charge on a test charge. So these are the main points that we have to remember when we consider the electric field and magnetic field due to a moving point charge. Please keep in mind the importance of different terms in this equation about acceleration field, radiation field, and its dependence on r. Similarly, the dependence of velocity field on r. And then we also derived the equation of total force acting on a test charge, which is at the vicinity of a moving point charge small q. I hope this portion is clear for you. Thank you.